Hey everyone, Jeremiah here. And if you thought choosing databases was hard, wait till you see what happens when 7 engineers try to make 3 programming languages talk to each other. Today, my team will walk you through how we are architecting a system to process 21 aircraft sensors in real time and prevent pilot fatigue incidents. I'll cover our system design, Susan will detail the tech stack, Brian shows the full architecture, and Jason explains design patterns, Janku justifies SOA, and Jeremy and Jaden will demolish the alternatives. So let's start with section 1, system design. We chose service-oriented architecture. Why? Because SOA lets us glue different technologies together based on what they do best. You need to analyze biometric sensor trends, Python ML. Need concurrent API handling, Go. Need real-time dashboards, React. Each service solves its specific problem brilliantly. With Docker, we containerize these services. They're independent but interconnected. No more it works on my machine disasters. Each service can be deployed, scaled, and updated without touching the others. Here's how components interact. Traffic reverse proxy sits at the front door, directing HTTPS traffic to our backend or serving the React frontend. The Go backend is mission control. It orchestrates everything. When edge nodes connect via MQTT with sensor data, the broker checks with our backend for authorization. The backend calls our ML engine through JSON RPC for fatigue analysis, stores operational data in MongoDB, while InfluxDB handles the time series telemetry streams through Telegraph. The data flow is clean. Sensor stream to MQTT broker, Telegraph pipes it to InfluxDB, backend queries both databases, ML engine analyzes patterns, frontend displays results. Simple, efficient, and scalable. Now, Susan will explain why we chose each specific technology in our stack.
Thank you, Jeremiah. Let's take a look at the technology stack that we will be implementing. For the backend, we will use Go, as it provides high performance, scalability, and concurrent performance that is necessary for our app's system requirements. Our front-end's interactive dashboard will be put together using React and Vite in the form of a single-page application. This simplifies state management and provides effective caching mechanisms to improve the user experience. The machine learning engine is responsible for fatigue analysis algorithms and will be created using Python, which is the prime choice for machine learning inference. For scalability and flexibility, our operational data will be stored in a MongoDB database, where the time series telemetry data will be stored using InfluxDB because InfluxDB is optimized for time series data storage. Mosquito is our message broker and will be used for real-time data streaming. Employing a broker simplifies connection and deployment. We will use Telegraph in our data pipeline processing for metrics collection. For the containerization layer, we will use Docker Compose for service orchestration. Docker Compose enables the once-off deployment of all services with flexible configuration options. Over to you, Brian.
Thank you to Susan for showing off our tech stack. Hopefully all of this information isn't overwhelming you, because there's going to be much more where it comes from, and this project is just growing and growing. So I'm going to show off our architecture, how all these components connect together, and hopefully this gives some context about how the server is actually sitting in production right on the VPS right now. So first, let's go over to our architecture diagram. So first thing I want you to notice, this thing looks kind of like a flowchart, so you just have to find where to start. You kind of start at the top here, this is how you get in, and then from here you can trace whatever happens, right? And another thing to note here, this is obviously SOA, this is obviously service architecture, because the way you know it is these services are very clearly distinct and separate from each other, and many of them perform diverse operations. For example, the backend, it's going to take care of our storage, it's going to take care of redirecting to all of our machine learning things. It's also going to be presenting statistics to the front end for what in the world's supposed to happen. So that's first thing I want you to notice. This is almost monolithic, but no, not completely not monolithic, because these are all different services, and we can do it this way because Docker is amazing. So let's trace through a few scenarios here. Let's say you just send a request straight to our domain, no URL or anything, you just type in our website name. You're going to land on the front end, right? That's because you sent a request to a path that's not matched by this /API thing. So traffic is going to redirect you that way. And your browser gets all of these things reasonably quickly because this is just static hosting. So the front end comes to you very quickly. And then you have a problem here. The front end, this thing can't really work on its own because we need data that can persist, and we need all kinds of state. You need to be able to log in, all those things. So that's where the backend comes in. And this is the reason we use the proxy, because every request that you send to /API will land on that backend where we have Go running with Gen that is going to handle it for you. And he comes in here. If it's an authentication request, it's going to send back a response with a cookie here, and your browser's going to know, like, okay, you're logged in. This is how the browser knows that you're in a session and stays in your session. And this is also for security purposes, because that cookie you can set so that the JavaScript itself on the browser can't even access it. So this makes it a lot harder for an attacker to leak out credentials from a logged in session, as compared to things like JWT. So, okay, off topic, let's go on. You send a request to that. Sometimes it just sends it straight back. There's some of the endpoints that are just, quick and simple. But there's obviously most of them have to actually do some heavy lifting stuff on the back end there. And the thing that so far has most of our attention is the general CRUD stuff. Stuff like you have to be able to sign up, log in, you have to be able to make new users, you have to be able to create new flights and edge nodes and everything like that. And that's when this thing sends its request over to MongoDB, right? But it happens through these store interfaces, and this is essential for the testing abstraction thing, which we have mentioned in the previous video, right? So it uses a store, it lands down here, and we're also going to have stores later that access the InfluxDB side of it instead, because as I said earlier, the backend is going to have to get some of those telemetry data to send it back as it's needed. But let's say the backend has to do something that's just a little bit above its pay grade, right? Because Go is a powerful language, but it's a very simple language, right? And that's the reason it's powerful. But sometimes you need a language that can just do everything for you, and that's what Python is, right? So we have the Python service, that's an ML engine that we have running there. And so when you have something that you really need that library for, things like the face embedding generation, or like we're going to do prediction stuff. Later we're going to predict pilot fatigue based off of environments. We're going to use all of these machine learning stuff to determine the best allocation of pilots to different flights, right? So these things have to happen in Python. They basically just have to. We're not geniuses. We can't implement these libraries ourselves because these are things that, unless you're studying them, it's above your pay grade. So we have a separate service here, and it connects with a Unix socket. So this thing boots up, makes this Unix socket file, and when the backend boots up, it connects on that, and whenever it needs it, it's going to send that request. We're using JSON RPC, so it's going to serialize that request in an agreed upon format, and then that's going to arrive at the other side, and then your Python's going to do whatever in the world it needs to. For face embeddings, if you have to go fetch it from MongoDB, fetch the image that you need from GridFS, and then it's going to have to use whatever inside face we have going on for that generation for the face embedding. Right. So as you can see here, we're showing off, you send the request, and then it returns the result. Right. And here's our different entry point. Most of our data, in terms of volume, is going to come in to Telegraph through MQTT. Right. So it's going to be sent over MQTT, which we also have encrypted, MQTT-S, with a shared certificate of report 8883. It's going to land there on our broker, and now our broker is going to obviously take that, decide what to do with it, and send it to all of the subscribers that are subscribed to that topic. And one subscriber that we'll always have is Telegraph. Telegraph is what we're going to be using for all of our persistent storage of telemetry data, or it connects to that. It's the reason it works. Our Telegraph is going to subscribe. It subscribes on all of the topics, and it listens on MQTT, and then it goes ahead and saves that in InfluxDB. So I hope this made this diagram make a little more sense. Okay. Now next, I'm going to show off just our IPC stuff. This is important for our service-oriented architecture, that this makes sense, because this is an essential architecture design question, which is, which kind of protocols are we going to be using? How are these things going to be interacting with each other? We use standard protocols because it's easier than having a custom one, obviously. So the most frequent one in our code base, in our system, is request response, right? So that means all of our protocols are asynchronous, right? So the person requesting and the person being requested both block. Like, you send the request and then you wait for it to be done, and then you get your things back. So it doesn't sort of just flow as it wants to, like asynchronous things do. And then on the other hand, we have the MQTT stuff, right? MQTT differs very much in this architecture because MQTT is a messaging service. So MQTT, this is asynchronous. It's just going to land wherever it does, whenever it wants to. And we're just going to handle that as it comes in, send that to the dashboard on the front, so that all of these things work together. Keeping most of the things synchronous is going to help us maintain all of the quality and structure, and it helps us to test everything. Because what happens with the request is, with a synchronous request system, is you get this sort of recursive structure. But requests make sub-requests to other services, and that simplifies knowing when a request ends and all those kinds of things, and it makes it easier to forward information. So that's all that I have for you. I was able to illuminate some of these concepts that we're using in our code base. And now, for some more context, I'm going to give over to Jason, who is going to be presenting our design pattern.
Thank you, Brian, for that absolutely wonderful explanation of the software architecture. That was immaculate. Hi, everyone. When you're building complex software like our Cogniflight Aviation safety system, we use proven solutions called design patterns. These are tested methods that solve common programming challenges. Let me show you the 5 design patterns which we implemented. First, we have the repository pattern with user store and edge node store. This creates a single organized way to store and retrieve all data. Instead of having data scattered throughout the system, everything goes through these dedicated storage managers. This makes our system more reliable and easier to maintain. Secondly, we have the factory pattern for session creation. When users log into our system, this pattern ensures that every login session is created using the exact same process. This eliminates errors and guarantees that all sessions or all user sessions work consistently across the platform. Thirdly, we have the observer pattern for alert notifications. This automatically sends notifications to the relevant personnel the moment our system detects pilot fatigues or other safety concerns. It ensures critical information reaches the right people instantly without any manual intervention. Fourth, we have the strategy pattern for role-based permissions. This gives different users access to different features based on their job responsibility. Pilots see pilot relevant information, ground crew sees maintenance data, and administrators have full system access. Each user gets exactly what they need. Finally, we have the Singleton design pattern for database connections. Instead of creating multiple database connections that could slow down the system, this pattern ensures that we just use one efficient connection that all services share. This improves performance and reduces system resource usage. These 5 design patterns work together to create a robust, efficient system. They ensure that our safety aviation platform responds quickly to emergencies, maintains data security, and operates reliably when pilots' lives depend on it. Now, this solid foundation allows us to focus on what matters most: keeping aircraft and pilots safe. Thank you.
Thank you, Jason. So, why did we choose service-oriented architecture? First, SOA gives us separation of concerns. Each service solves its own sub-problem. That means we can work on parts like the machine learning engine, back-end, and front-end independently without stepping on each other's toes. Second, it brings scalability. If the system grows, we don't need to scale everything at once. We can scale only the service that's under pressure, like the machine learning engine when more aircrafts are connected. Third, interoperability. This was key for us. SOA allows completely different technologies to talk to each other through a well-defined interfaces. This is how we were able to connect Python for machine learning, Go for backend APIs, and React for the dashboard, all in one coherent system. Next, we get reusability. Once a service exists, it can be extended or reused in future features without redesigning the whole system. Then, maintainability and flexibility. Because services are semi-independent, we can update or experiment on one piece without breaking the rest. That makes it much easier to evolve the system over time. Finally, configurability. SOA is broad and adaptable. It gives us the freedom to design around our exact aviation needs instead of being boxed into a rigid structure. On the right, you can see the benefit visually. Different technologies working together, but loosely connected, so we keep control while staying flexible. That's why SOA was the clear choice for us. It balances complexity, flexibility, and future growth, while meeting the safety demands of real-time aviation monitoring. I'll then hand over to Jeremy for the justification of not choosing the other architectures.
Good day, ladies and gentlemen. My name is Jeremy, and within this portion of the presentation, we'll be focusing on the justification for not choosing other types of architectures for this particular project. Let us begin. The first architecture we did not choose was the layered architecture. Here are the reasons why. The first reason in this case would be that it creates performance bottlenecks. The rigid hierarchy would introduce unacceptable latency for processing real-time sensor data, which is critical for immediate detection of fatigue on the pilot. This is very crucial, as even missing it by a millisecond would cause real-time dangers for the pilot, the passenger, as well as the plane. Secondly speaking would be that it prevents direct data access. The strict communication rules would block the machine learning engine from accessing the telemetry database, which is in the InfluxDB, directly, forcing slow and unnecessary data marshalling through intermediate layers. Number 3 would be the inflexibility for diverse technologies, integrating our different tech stacks such as Go, Python for machine learning, as well as React for our front-end, would then become cumbersome when each must conform to rigid layer boundaries instead of communicating freely. And lastly, the fact that it hinders optimization. The architecture's lack of flexibility would make it impossible to optimize critical data pathways for achieving sub-second alert generation times. The second architecture we rejected was the microservice architecture. Here are the reasons why. The first reason would be the excessive operational complexity, because as it manages dozens of fine-grained services, it would require sophisticated orchestration tools such as Kubernetes, which is then overkill for our current team and our project scope. Secondly, it introduces network overhead. The distributed nature creates significant inter-service communication latency, which could impact the millisecond sensitive requirements of our real-time safety alerts. Number 3, it complicates debugging. Tracing a single request or investigating an aviation incident across many distributed services will be extremely challenging and slow. And lastly, it's quite unnecessary for current scaling. The benefits of this architecture are outweighed by its overhead for our system size, making it an overly complex solution that doesn't overly fit our goals in this case.
Hello, my name is Jaden Crossan. So first up, I will discuss serverless architecture and why this won't work for our system. So firstly, serverless introduces cold start delays, which can take several seconds. This is far too slow for real-time fatigue monitoring, where every second counts in aviation safety. Secondly, our machine learning modules require persistent state and high memory and CPU resources, which exceed the limitations of serverless functions. Thirdly, serverless platforms have 15-minute execution time limit, or flight sessions run for hours, so this makes it completely impractical. Another issue is cost. Continuously telemetry streams would mean millions of function invocations, which becomes very expensive very quickly. Finally, maintaining WebSocket or MQTT connections for real-time streaming in stateless environments is problematic, and our complex ML interference pipeline simply doesn't fit into the simple function model serverless provides. So overall, while serverless is flexible in some cases, it's not viable for our continuous real-time aviation workload. Next up, we'll have a look at event-driven architecture. This model is good for telemetry streams, but making everything event-based would overcomplicate basic synchronous operations, like user logins, API calls, and dashboard queries, which all require immediate responses. It also makes simple CRUD operations unnecessarily complex, and debugging asynchronous change of events is very challenging, especially when we need clear audit trails for aviation safety investigations. Another drawback is eventual consistency model. For us, we need immediate authoritative alerts when a pilot shows signs of fatigue. Delays could be dangerous. On top of that, adopting full event sourcing means training our team and complex patterns and managing event schemas, which adds unnecessary overhead. Lastly, we need sophisticated event orchestration and correlation logic, which could increase system complexity without giving us enough benefit for a mix of real streams and traditional requests. In short, while event-driven has strengths, a pure EDA is not the right fit for our safety-critical mixed workload system. Thank you so much.
Alright, thank you Jaden. Let's bring this architectural masterpiece in for landing. And unlike Boeing's recent track record, we're aiming for a smooth one. Look, we could have built this a dozen different ways, but here's the thing. When you're monitoring whether someone operating 300 tons of aluminium at Mach 0.85 is still cognitively functional, you don't experiment with trendy architectures. You pick what works. We evaluated 4 other architectures and systematically destroyed each one. Layered, too slow for real-time telemetry. Microservices, we'd still be configuring Kubernetes while planes are falling. Serverless, sure, let's add cold start latency to safety critical operations. Event driven, because nothing says emergency response like eventual consistency. SOA emerged victorious because it respects physics, economics, and our sanity. It scales when needed, adapts when required, and most critically, it's done before semester ends. Hopefully. So that's Cogniflight Cloud's architecture. A system that reads biological stories from sensor streams, predicts fatigue before pilots feel it, and might actually prevent someone from becoming a cautionary tale in aviation history. Thank you for surviving all 4 presentations. Your patience is appreciated almost as much as pilots appreciating not crashing. Remember, in software architecture, as in aviation, it's not about building the most complex system. It's about building the right system. And sometimes the right system is the one that keeps planes in the sky and developers sane. We are planning to achieve at least one of those. And have a lucky day.